Okay, welcome everyone to my continuation of what is algebraic graph theory. Today we would like to dive deeper into random graphs. So we'll discuss various models of random graphs, and we will use them in further videos, future videos, to kind of prove kind of cool statements. So random is really kind of saying what are the properties or properties of random graphs. This is kind of the same as what are the properties of essentially all graphs, right? So we want to make sure that we have some models, and they're essentially all the same, but as you will see, they're kind of different. But I still like them to explain them because they're essentially two different approaches, or three. There will be a third one, but I'm not going to use the third one that often, but it's certainly worthwhile to be mentioned. So the two approaches I have in mind are top to bottom and bottom to top, whatever that means. So let's have a look what those are. Top to bottom first. And I usually denote them by G, N, M. So N is always a number of vertices, and M in this case is also a number of vertices, but of a sub-thingy. We'll see that in a second. So I really like to think of this picture here. We have some choice involved, and I want to kind of make everything kind of equally likely. So I really have this picture, and I don't like the other ones here. So equally likely is really the first picture. And what I do is I kind of take the complete graph on n vertices. So n is my complete graph. And I just put all subgraphs with m edges in a bag. And I just screw my back, just turn it around and pull out a random graph, right? Randomly. And everything is equally likely. So that's really this picture. Everything is equally likely to appear. And the random graph I get is denoted GNM. That's, of course, a bit vague. The random graph I get just has a certain probability to be a certain type of graph, but I will still say this guy is the top to bottom graph. And why do I call it top to bottom? Because you start with the parent graph, the Kn, and then you kind of take out a kind of a subgraph with m edges, right? So that's kind of the top to bottom approach. And we make everything equally likely. Okay, sounds pretty nice. Makes sense for me. But the next one, I actually like it a bit more. It makes somehow more sense for me. So let's have a look. Well, clearly this is now, well, clearly whatever. This is now the bottom to top approach. And it's more related to really rolling a dice or flipping a coin. I usually call them coin flip graphs. And I will denote them by G and P. P is some probability. So I will mess around here actually and make some graphs more likely than others. Anyway, I take a probability, and n is still the number of vertices. And now I start from the bottom. So here I started from the complete graph, let's say on 3 vertices, and just produced my GNM exactly. And now I start with the empty graph, let's say on whatever 3 vertices, and I produce a GNP. And the way I do it is I take every pair of vertices, and with probability P, I put edge. So that's where my P comes from. And I don't put any loops, so I only take different vertices, and I just put an edge with probability P. Right? So that's really like for every pair of vertices, you flip a coin. If its probability is 50%, you roll a dice, depending on the probability, or you just ask your favorite computer algebra program to get you a random number. But that's essentially what it is. And I call this bottom to top because we kind of add edges randomly. While in the other approach, the top to bottom approach, we start with something and kind of take out graphs. I hope that makes some sense. And they look, obviously they're different, but it can somehow show that they somehow behave in the same way in a certain sense. But let's ignore that. Let us talk about the third model, which I'm not going to use that much. So these 3 models, the third one is still to come, are kind of the standard models that you use. And you get slightly different results. We'll see that throughout the next few videos. But anyway, the last one is an evolution, and n is still the number of vertices. And it's really the picture of, in evolution, there is some choice, and essentially evolution randomly chooses well to do something. Just if you think this is there are so many crap choices evolution did. Oh god. Anyway, so here you have a good example. So here's those birds, and well, they can kind of develop in a different way depending on whatever kind of environment they have. But for this video, I just think of evolution as being random. So randomly, there will be some evolution of those birds, and you get different types of birds. And that's what we will do for the graphs as well. We kind of mimic evolution in terms of graphs. And really, Gn is in this case a sequence of graphs. And we have n vertices. We again start with something with n vertices and being empty, right? So the subscript here is the number of edges. And then we randomly increase it, put in another edge, put in another edge, put in another edge, and we stop somewhere at some subscript. So it's really, this is one of the steps. So let's say this is 1, 2, 3, 4, 5, 6. This is G6, and I hope I haven't miscounted, and it should be G7. And this sequence itself is the random graph, and we just do it in the way that every sequence is equally likely chosen, going by convention. Okay, so this is really mimicking evolution, which I think is kind of fun, but they're also a bit more difficult to describe than the other ones. So I usually won't use them so much, but I think that's kind of a cool idea. So we have kind of 3 models, top to bottom, bottom to top, evolution, and whatever your favorite one is. This one is a bit easiest, I think, so I just like bottom to top most. So, and because I'm very biased, most videos then will focus on the bottom to top ones. I'm very sorry for that, but I guess we are all biased here. Anyway, so let me give you an example of what happens here. So we have this expectation, which I call by the must be E, and we have, let's say we just discussed the bottom to top and the top to bottom graph. So EM and EP. And what is the expectation of having a complete subgraph of size S in your random graph? And that's kind of the right question to ask, because the random graph, I just always say the random graph, but it's actually more like a probability cloud of graphs if you want. But anyway, you can easily compute that. So here, for example, the probability to find something, and it looks very similar, but it's slightly different. That's what I mean, right? So kind of, if you ask those questions, what is the probability to, in this case, find complete subgraphs of size S? There is an expectation, and well, you can usually compute that and get some nice result. And it's really, really nice. In some sense, everything depends, as you can already see in this example, kind of crucially on the chosen model, but in some sense, it also doesn't depend so crucially on the chosen model. So if you fit in here real numbers, you will see that the behavior is essentially the same, although the formulas look very different. And that's what I kind of mean by the models are all different, so you get slightly different looking formulas, but the overall pattern is kind of built into randomness itself, so the overall pattern usually doesn't change too much. And these are the questions we would like to answer. So what is the expectation of blah? What is the probability to find bloop? Something along those lines. And this is actually quite nice. So you can answer this relatively simple question in a, well, not too bad closed formula, right? It's not a bad closed formula. So if there's something n over s, p to the s, where s is just shorthand for this one, for example. And I just listed them, and it kind of depends a bit. So kind of fun. These graphs behave, or these random models behave relatively similar for certain choices, but of course there are choices involved, and if you don't do the right choices, they're really different. So if, for example, if I take p equals a half, which is kind of the coin flip graph, and I look for subgraphs, complete graphs, which have roughly n over 3 vertices, then I get this curve here. So I get this little curve when n increases. So that's what it is, okay. So what are that's the expectation value. So this is my capital E, similar for the bottom picture. And I would get exactly the same graph. I mean, spot on the same graph for those choices for the bottom one. And I could do something similar. I could vary my P with N, for example, and eventually just the probability just drops to 0, and I would get the same for those two. So although they look different, they somehow do the same. And although the formulas look different, there's something built into randomness itself. And you can just, it doesn't really matter which model you take, you somehow always get kind of the same result, because randomness itself appears here, and just the precise formulas are different. So keep that in mind when we discuss kind of really cool and sometimes surprising kind of how likely is it to, for a random graph, have property X. We'll see somehow different formulas for the different models, but they're all essentially saying the same, and I will stress that as we go along. So what we can see here, for example, is so the probability to find those is very, very big in a certain range, around 10, and then it kind of drops. And here it kind of obviously drops because I put fewer and fewer edges. Let's focus on the first model. Fewer and fewer edges because my probability drops quite a lot. Anyway, I hope you enjoyed this video, and I also hope to see you next time.